In this video, we're going to look at the topic of Lewis symbols and see how Lewis symbols can help us understand aspects of bonding. In section 8.1, we're introduced to the idea of Lewis symbols. Here we see various electron configurations, and below them, the Lewis dot symbol. In the Lewis dot symbol, the valence electrons are placed individually until you reach 4, and then you start to pair them up. So for chlorine, 7 valence electrons, 1, 2, 3, 4. Then I'll begin to pair them up. This would be the Lewis dot symbol for chlorine. It doesn't matter if the single dot is pointed to the right, down, but you need to make sure you have the correct number of valence electrons shown. The Lewis dot symbol clearly tells us the number of valence electrons, but it tells us more than that. It tells us whether we have lone pair electrons. Those are typically not involved in bonding, or unpaired electrons, which are. So if you look at the various Lewis dot symbols, we can see that carbon will usually form 4 bonds, chlorine would form 1 bond, nitrogen, if I look at the Lewis dot symbol, 3 bonds. When it comes to Lewis dot symbols in these patterns, do you understand what's going on? Can you draw Lewis dot symbols? We're going to begin to use them as described in section 8.3. In molecular substances, the atoms are often bonded together by sharing electrons. Let's consider the simplest case in H2. Each of the hydrogen atoms has an unpaired electron, and in a covalent bond, those electrons are shared between each of the atoms. That could be shown with 2 dots or with a line, where a line represents 2 electrons that are being found between the atoms. Physically, what's going on? How would this lead to the atoms sticking together? Well, the nuclei are positive, the electrons are negative, and if electrons are found in the region between each atom, then they can form sort of a glue by being attracted to both nuclei at the same time. That's what's leading to the formation of the bond. We could have the case where the electrons are shared between 2 hydrogen atoms to form H2, between 2 chlorine atoms to form Cl2. One pattern that we see is what's called the octet rule. From some elements, when they're bonded together, they tend to possess or share a total of 8 valence electrons. If I were to count for chlorine here, I would see 1, 2, 3, 4, 5, 6, 7, 8, a total 8 around this chlorine atom. For the other chlorine atom, 1, 2, 3, 4, 5, 6, 7, 8 as well. That's an application of the octet rule. In the case of hydrogen, it's easy. Hydrogen will only form a single bond. What are the Lewis structures for these common molecules? Well, to begin with, we can recall what the Lewis dot symbols were and recognize that hydrogen forms 1 bond typically, or always, carbon 4, nitrogen 3, oxygen 2, and fluorine 1. So if we put together the parts for that, we would see then the Lewis symbols and the Lewis structures for the molecules HF, H2O, NH3, and CH4. We need to be able to quickly draw, recognize, memorize Lewis structures for common molecules like these. These all are examples of Lewis structures with single bonds. You can have double bonds, triple bonds. In each case, the line that we're drawing represents 2 shared electrons. So in the carbon dioxide, I see a total of 1, 2, 3, 4 electrons in this region. 1, 2, 3, 4, total of 4 electrons in this region. When I refer to bonds as being single, double, or triple, that's the bond order. A single bond has a bond order of 1, a triple bond a bond order of 3. For these simple molecules, I think we can simply put them together based on the number of bonds they usually formed. But we're also going to need a pattern that will work for any molecule. Let's try this question. This is a self-assessment from the textbook. It's given us a Lewis structure. It's showing how the atoms are connected, but it's not providing all of the remaining details. For example, I don't see any lone pairs there. What would this one look like after we add in all of the remaining electrons? So in order to do this, I would first recognize how many bonds they typically form and how many lone pairs they have. Take a second, see if you can get started on this problem. What are you able to do? What questions do you have? As I look at it, all of the atoms that I've circled here, I think they're fine as is. Hydrogen forms a single bond, and I see that taking place. Carbon forms 4 bonds. It's taking place for this carbon atom. The other atoms, I think I need to add some more information. These oxygen atoms on the left and right, they form 2 bonds, but notice they would also then have 2 sets of lone pair of electrons. So I'm adding those to the picture. After I do that, I think those look fine too. For the other carbon and oxygen atoms, let me add the electrons that they initially had. If I do that, I see that if I shift in an electron from each of the oxygen atoms and shift in an electron from each of the carbon, that will give me double bonds, and now everything seems to work in my picture. My answer then says that I have 2 double bonds and a total of 8 non-bonding pairs of electrons. Let's count those up. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 non-bonding pairs of electrons. What would be an approach that will always work where we don't have to rely on how many bonds they typically form? Here's the outline that the textbook gives us. Let's follow through an example or two with this. So the very first step in the process, we need to determine the total number of valence electrons. So this is a different approach. We're not going to worry about which element, how many electrons it initially had. We're just going to add up the total number of valence electrons. If we have an anion that we're looking at, we'll just add another one for each negative charge to the mix. And for a cation, we'd subtract one. Next, we're going to make an initial sketch and show how the atoms are connected using single bonds. This is a key step here. Many times the formula will tell us the relationship for how the different atoms are situated. So we might want to look to that detail. Another thought, for polyatomic molecules and ions, the atom that goes in the center is oftentimes written first. One more piece of information, if we consider, for example, the bonding here in carbonate, oxygen forms typically 2 bonds, carbon 4. It's going to be helpful to put as the central atom the one that can branch out and form the most bonds. If I put oxygen in the center, it would limit how many bonds that I can then form. So that's another way of seeing for carbonate, the central atom is going to be carbon. We'll then take those total number of electrons, having put some into single bonds, and then complete the octets around all of the atoms bonded to that central atom. If we have any left over, we'll place them on the central atom. And if we reach the end there and we find we don't have enough electrons to make the central atom an octet, we can shift the electrons to make multiple bonds. Let's work through an example. So if you've tried this before, or you want to give it a try, see if you can draw the Lewis structure for this molecule, CH2O. Okay, let me show you my work on this one. If you have questions along the way, add them as comments. So I'm going to, first of all, look to the periodic table and determine the total number of valence electrons. I'll make my sketch and I'll put carbon in the center. I'm adding then single bonds. Each single bond corresponds to 2 electrons. I'll take the electrons that I have and complete octets for the outer electrons. For hydrogen, it can only form a single bond, so those are all set. That accounts for all of the electrons. The central atom, however, did not have an octet, so I would switch 2 of the electrons, shift them in from the oxygen to form a double bond. Now I think I'm all set. What questions do you have on the process here? Here's another one, drawing the Lewis structure for phosphorus trichloride. What I'd like you to do is give this one a try working through the steps. Or if you're confident, give it a try without referring to the steps. To explore this one, let's see what the discussion is within the e-text.
Draw the Lewis structure for phosphorus trichloride, PCl3. Here is the procedure you should follow in drawing Lewis structures. Let's solve this problem starting with the first step. Phosphorus trichloride is neutral. Since it has a charge of 0, the charge does not have an influence on the number of valence electrons. Phosphorus, which is in group 5A, has 5 valence electrons. Each chlorine, which is in group 7A, has 7. The total number of valence electrons is therefore 26. Second, we arrange the atoms to show which atom is connected to which, and we draw a single bond between them. Phosphorus is the first atom in the chemical formula. In binary compounds, the first element in the chemical formula is generally surrounded by the remaining atoms. So we proceed to draw a skeleton structure in which a single bond connects the phosphorus atom to each chlorine atom. Third, we add Lewis electron dots to complete the octets on the atoms bonded to the central atom. Completing the octets around each chlorine atom accounts for 24 electrons. Remember, each line in our structure represents 2 electrons. Fourth, recall that our total number of electrons is 26. We place the remaining 2 electrons on the central atom, phosphorus, which completes its octet. This structure gives each atom an octet, so we can stop at this point. This gives the Lewis structure for phosphorus trichloride, or PCl3. Use the procedure outlined in this video, which is also listed in the chapter, to draw Lewis structures.
So the best way to become proficient and understand the process is by doing it. Here are some end of chapter questions for you to try. All of these are consistent with the ideas that were shown within this video lesson. Give these a try, see how you can handle it, and we'll build from this. This is a skill that we're going to be using both in this chapter and other ones as well. We'll be adding additional information, so it's going to really be beneficial to start practicing now.